Tonight, we're going to talk about digital amateur television. I come from a rich background. I've been working in the industry. I just lost my job last week. After 27 years, I'm now retired. But so what I've been doing for the last 27 years is to launch broadcast television, ATSC, that kind of stuff. So it's what you're watching today, over the air broadcast television. We're going to talk about kind of the broken into these parts, starting with who, what, where, when, why, kind of like how did we get here kind of thing. Then we're going to step into a little bit of coding and compression technology because that's integral to doing digital. And then we're going to talk about those systems, the stuff, the parts, the pieces, when you put it together, what does it look like? And then we're also going to step into some streaming solutions and then wrap it up with this summary. So what is TV? What is TV? What is DATV? Well, what is TV? It's a bunch of moving pictures. So in the back, history, when we were doing this first, it was this analog thing that I alluded to. You could buy a TV, tune it to channel 57, I think it was, or 47, one of those two. And it would end up at 427.25. That was the frequency assigned to cable TV channel, whatever it was, 57, 47, whatever. The bottom line was, it was a clever trick. Otherwise, you had to have, frequency converters. But television was pretty much ubiquitous through the United States. Everybody had a television at some point. Maybe some of them were color. A lot of us grew up with black and white, if you're a baby boomer like myself. But so it was leveraged in the early days to do, well, and we all called it fast scan television. We knew it took 6 megahertz. It was just pretty much the analog derivative of what a regular broadcast signal was. And so we started from all this from a long time ago. In fact, it was so cool to see this picture over here on the right side. This is some guy up at his lofty perch in Baton Rouge, Louisiana. He's such an amateur, right? The guy wearing the tie that has the pocket neckerchief, right? That guy. So, ham radio operators, they did it with class back in the days. So we need to talk about where we came from. So we came from the standards that drove those systems for NTSC and PAL and all that kind of stuff. And this came from what was deployed around the world. As you see in North America and down into South America, NTSC was widely deployed, where other places it was PAL or CCAM or some combination of that. But so those systems are what we had to be able to start from. And it was all predicated on how the spectrum was being managed. So here in the United States, there were these blocks of frequencies that were chunked up into 6 megahertz allocations. And each of those allocations represented a channel number, the dial that you would, tune the TV with. So you go clunk, 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 and you would change the channel. So these were the individual 6 megahertz allocations across the TV dial. So analog TV is fine, so why use digital? So everybody knows that NTSC, PAL, it doesn't matter. It was essentially the AM radio version of television. It, in fact, is amplitude modulation signal FM audio, but amplitude modulation video was that you could see a disturbance in the picture from, lightning crashes and things. But it was an effective system. It was NTSC 6 megahertz wide, was allowing broadcast television to deliver 30 frames per second or 60 frames interlaced, but that's a technicality. The point was, it was actually very robust system. In fact, so robust, ham radio operators were able to see 2-meter media scatter and would know this when they could see channels on their channel 2. So they take the TV and in their market, wherever they are, somewhere up in Montana, it doesn't matter, they would tune the TV to channel 2. And every once in a while, they would see the glint of a TV picture. That's because it's up near the 6-meter band, and they were seeing meteor scatter that would allow the signals to reflect from another market, and it would show up on that guy's TV, and then he knew he was in the middle of a meteor scatter event. But today we live in a world of Ultra HD, so we need ATSC or DVB, and so all these are these systems that were defined to be able to modulate digital over a carrier using COFDM or QAM, Qpsk, whatever. And we'll talk more about that. So the differences are that analog, though it was, this really clever system, it was standard definition only, meaning we live in a world of high definition, television today, the pictures are clear. So back then they were only so big. Well, if you remember, the TV picture tubes kind of maxed out at about 25 to 27 inches. It was only a matter of time before they started working and developing larger tube technology, and then eventually flat displays, LCD and so forth, plasma, that allowed the screen sizes to really take off. So if you remember, standard definition is where we came from. It only supported one channel at a time. So when you turned to that channel, you got that channel. And it, of course, required 6 megahertz. Obviously, if you're in Europe and other places, it's even wider, 7 and 8 megahertz. It's easily distorted by reflections. You would have to, change the rabbit ears and try and get a better picture and all that kind of stuff as atmosphere changed. But it was minimal processing requirements, low cost to start up, and requires less power density because it's based on what was in the picture. And so whenever they went to full black, that's when the transmitter went to full power, but the TV idled. That's why there was always fade to black. But then they didn't stay in black very long, and then they'd go to the commercial, and then they would start transmitting with power. So when the transmitter station was transmitting white, it was actually transmitting less power, but the TV would use more power. So it was flipping the model of where the energy was. Okay, now we're digital. So digital has a buffer delay. It introduces things like artifacts when you get bit errors. It adds more processing. Obviously, there's a computer involved in here, kind of thing. There's this steep learning curve. There's a bunch of math, tons of things going on. It's, we're standing on the shoulders of giants when we're talking digital television, because there's all these different patents and technologies that are put together to make it work. The digital signal has a cliff effect. You either have a lock or you don't. And the second you go over that cliff, you don't have a signal anymore. And so it needs a sequence of packets in like about 3 seconds long of good before it'll start back up. So it really needs to have a good positive lock. But when you do have a lock, the pictures are always perfect because they're compressed. And we'll talk more about that. The main takeaway, and everybody should understand this concept, is it introduces what's called multiplexing. You know how when you turn on the TV today, you go click the channels, you see like 12.1 and 12.2 and 12.3. Those .1, .2, .3s is because they're multiplexing channels on the same carrier. And that's why you see this huge number of channels. So if you scan your TV, you'll see more channels today than you ever have. The broadcasters keep adding channels because they make more money. Every time they turn on a channel, they make more money. It's that simple. So broadcast digital television has proliferated around the world, almost everywhere, except for parts of Africa and this one, place called Afghanistan, but who's counting, right? The United States and South America and all Brazil, all these places, they all already have digital standards. Everybody is almost completely transitioned over to a new system, whether it's ATSC or DVB, that's not matter. Everybody's gone digital for the most part, with the exception of the places in Africa. So here in the US, we broadcast digital TV using ATSC 1.0 or 3.0, and we'll talk about that. ATSC is the Advanced Television Systems Committee. So a thing just happened, and this was from about 5 years ago. The FCC did this thing where they auctioned off spectrum. They're in a habit of doing that because when they do that, that's like charging revenue. They're making money for the US government. So who's buying the spectrum? the phone company. So what happened was they did this reverse auction thing, and so it started at the very top and worked their way down, and they got to a place when the rules of the reverse auction were met, and this is where it ended up, where now broadcasters have a total of 210 megahertz, and this is the channel lineup. These are the channels they have left. It stops at channel 36. Notice there's a channel 37. There's always been a channel 37, but has anybody ever seen a channel 37? And the answer is no. That's a radio blacked out channel. It was just an assignment. They left 6 megahertz carved out, but nobody has ever been issued a license for channel 37 because the radio telescope guys use that frequency, and so it's a carve out. Anyway, this is what we're left with today in broadcast spectrum. 1.0 ushered in the transition from analog to digital. So they shut down analog in 2009. And then in 2020, during the pandemic, all the last of the low power stations, the really rural market guys, they had their shut off date, just so they expired too. So now there is 0. So 2009 was for the full power guys. The full powers are the the big stations, and so they were cut over in 2009, and then they gave everybody else 11 years to clean up and finish up and get their work done, and so forth. So once 1.0 happened, it allowed the repack into less spectrum. So then they did the repack. Then all along at the same time, there's been this competition for streaming. Everybody knows what Netflix and YouTube is, okay? It's very common to talk to people, and they tend to now spend more time on streaming services than they do on over-the-air broadcasts, unless you're like me, a boomer or a Gen Xer, or somebody like that, somebody that's older. The millennials, they're glued to their TikTok and their cell phones, and you know what I'm talking about. Okay. But so 1.0 was put together by the Atsc committee over the span of about 10 years. Started approximately 1996. So by 2006, everything pretty much had been cut and dry. And so there were stations that were already implementing early design that had already gone on air in many of the markets. But 2009 was the cutoff, and that's when everybody had to finish those systems. But those were the old MPEG-2 systems. In today's standards, those are old systems. Since then, the standards have evolved, the display technology has evolved, everybody's kind of moved on, okay? So then we came up with what was called the ATSC 3.0 standard. So there's a little bit of background history here. There was a jump from 1 to 3 because there actually was some work that happened that would have created ATSC 2.0, but it was too little too late. And so the decision was made to just move on. And so we went to 3.0 as a non-backwards compatible system. So while they're transmitting 1.0 today, we came up with the next standard, which was to leverage the latest in technology. So it moved away from MPEG-2 to HEVC and Dolby AC4. It included things like dash packaging. We'll talk about that. But so the point is, it leveraged all the latest cool tricks that can do. One of them was in broadcast television, they have a thing called physical layer pipes. So the ATSC 1.0 signal is a 19.392658 megabits per second physical layer pipe. So it's one pipe, okay? The difference is the 3.0 system allows you to have more than one physical pipe. Now there's some trade-offs and there's some caveats in there, but the point is you can have more than one pipe definition, be at different robustness levels, different base modulation, using different time and frequency and layer division multiplexing schemes. 3.0 has lots of knobs, is one way to put it, where in 1.0, there were no knobs. The whole point of 1.0 was just a transition from analog to digital. But now we're digital. But what the industry needed, and what I'm saying we needed because I was part of the industry, the we part was we wanted as many flexible elements now that we're already digital, so that we could do things like deliver the signals over one or more transmitters. They like this technique called SFN, single frequency networks, means you can have multiple towers all running on the same frequency, but they're phase aligned so that all the transmitters emit the same bit at exactly the same time. And so it creates a certain pattern which doesn't interfere unless you live in one of these particular places, in which case they try to null those places out. But the signals become additive. And so with more transmitters, then you get a better coverage pattern. So it's of great interest to them. This SFN is a big thing. It allows you to spread your signal out geographically to help improve the coverage instead of having lots of power on a high power, high tower situation. So the other thing you can do is, with this similar technology that they use for SFN, is to be able to bond to carriers. So instead of just one frequency on 6 megahertz, say channel 6, you can have another one bonded to, say, another transmitter on channel 8 or channel 14 or whatever. They are bonded metaphysically, meaning they know about each other in metadata, so that the combination of the packets of the two transmitters looks like one big virtual PLP. So it's like one big pipe. What would you do with a really big pipe? You'd put lots of television service. The other cool thing that 3.0 is because they use this DASH technology. DASH stands for Dynamic Adaptive Streaming over Hypertext HTTP. And if you know what HTTP is, well, that's what you use in your browser. So the whole point of this was DASH streaming is a technique that YouTube uses for streaming content. And so 3.0 has DASH packaging built into the transport layer, and they came up with a way to be able to transmit DASH over the air and at the same time stream it over the top. That's why we call it OTA plus OTT. Over the air, over the top. Over the top is the way they describe the streaming market. It's Netflix, YouTube, that kind of stuff. All right. So why should hams use ATSC? I'm not advocating. It's just that it's a technology. It's the basis of where this industry came from here in the United States. You would do this only to leverage the tuner that's built into the TV. Well, so the tuner that you have in your TV right now is an 8 VSB tuner. Would I recommend hams use 8 VSB? No, and I'll explain why later. But 1.0 just by itself means a new modulation, it's compression, it's transport stream, it's got all this technology. So it's more than just 8 VSB. It also includes PSIP tables, has this fixed PLP thing as a base transport. So there's all these things, when you add them together, create what's called ATSC 1.0. So for example, 3.0 had that similar concept when they came up with the standards. There's like 16 base documents that when you put them all together, it makes you, it allows you to broadcast 3.0, but they come in different parts and pieces. And so the point is, maybe what ham should do is, and look at the parts and pieces, because we can leverage some parts. We don't need all the pieces. I wouldn't encourage anybody to have to, use, a consumer television when there's other choices available. And we'll explain why in a little bit. So 3.0, as it was designed, was obviously tilted towards ultra high definition to get you to buy a new TV. That's what the whole point of this TV industry is to get you to buy a new TV. And the cell phone people are trying to get you to buy a new phone every 2 years. You understand this concept, right? I mean, we're all trained little puppets to, making certain we, go out and spend money. Well, 3.0 modulation is way more superior than 1.0. So if I was suggesting to use ATSC, I would prefer that we look into and do research on the modulation specification and not worry about some of the other pieces. And this is why I have this presentation. So I'm now going to start explaining why all this is done a certain way. Oh yeah, by the way, if you lived up here in the Bay Area, you know the problem we have. It's because we live near a certain Air Force base, and they have this thing called pause, which has darkened the 440 band. So we're not allowed to use a amateur television repeater on 440 for the simple reason is pause will see it. It's that good of a system. The, you know, pause was designed to be able to track these little tiny objects in space that might come into contact with one of our satellites or kind of fall on our head. So we want pause. So we had to turn off a bunch of 440 equipment up here. And so that's not true everywhere. It's certainly one of the things you guys can do down in the desert. You're much, much farther away from the Air Force station up here. So you can get away with it, but some of us can't. So you have to be careful about getting coordinations. I just wanted to make certain we touch on that point. So we need to wrap up part one here. So I wanted to quote Don Rotolo. He wrote back in June 2004 in CQ magazine an article about DATV, in which case he said the kind of project is this one is perfect for an active ATV group. Why? Because it requires a bit of money and expertise, but in the end, you will get a huge payback on investment because the upgrade is actually pretty minimal from the current ATV system's capacity you have now. What you'll get out of it is multiplexing, and we'll explain now. So part two, we're going to talk about how did we get here, and that's the compression and that's coding. That's actually two different things, but we'll get into the reason why. But first, we have to talk about what is a TV channel. If you remember back in the old days, you turn the channel, you got CBS, Fox, and NBC, and so forth. By changing the channel, you saw a channel. Well, so it actually means two things. One of them is to describe the carrier, like you're tuning the knob, okay? And that was a frequency assigned by the FCC. But at the same time, it also refers to when you turned on the TV, you turned on channel 4, you were watching a program, you know, whatever it was that you turned on to watch, you were watching a program on a certain channel. So when we say TV channel, there's kind of this blur between the two. One is a carrier, but one is a program. Okay, so we need to separate those two things. So when you turned on analog TV, oh, I see the thing rejustified my space over here. You had a video camera, you fed it to a modulator, you fed it into a power amplifier, and that's what fed the TV. Pretty straightforward. It's not rocket science. In an ATV receiver system, you have to have an antenna, one for each band. You might need a frequency converter, but there was usually a low noise amplifier to help pick up the gain. And then you fed it into a cable tuner receiver. So there were people that made these converters that would convert from other bands, 900 megahertz, 1.2 gig, and so forth, and put it in the cable tuner space. And then you would, between the converter and the cable tuner, you could find your amateur television repeater. But so now systems are leveraging these things. I see a message in chat. Maybe that's for me. Let's see what it says. Unfortunately, family need are occurring. I must miss the meeting. Bummer. Stefan, we'll miss you. All right. So we're going to now talk about what we're doing in amateur radio by leveraging some of the parts and technology that are available to us. If I can get it to forward. Oop. Oop. There we go. And there we go. So digital TV is based on multiplex data. And why do I say that? So here we've got two encoders. What does the encoder do? It takes a video and an audio input and compresses them into a bit stream. Let's say this encoder is set to 2 megabits and this one's set to 2 megabits. and that when you take the 2 megabits from this guy and you multiplex them with this guy, then you get a feed going to the modulator for a total of 4 megabits. But so the reality is there are bits that are video, and then there's bits that are audio, but they're multiplexed into 1 bit stream at the same time. So if you were looking at the bits as they're flying by, most of them are video, but every once in a while you'll see some that are audio. And those bits are mixed in with these bits. And so the sum total of all those bits is what's fed to the modulator. The modulator is the converter that takes the bits in the stream to convert them into changes in waveform. The waveform is what's being modulated to air because, of course, everybody understands this. You cannot transmit bits, like square waves straight to air. That's like a spark transmitter. Okay, so we're not going to do that, right? You're going to use a modulator. Okay. So one encoder is doing video and audio. It's fed to the multiplexer, and off you go. So the cool thing is we learned some things along the way. And what we were able to do was these encoders have the ability to see things in the video. And when the only thing in the video that, let's say it's a static slate of, 1-800 Ginsu knives or something like that, the encoder's not having to work hard. But let's say encoder number 2, it's a bowling game or something like that. And encoder number 3 is a game show and the lights are flashing. And encoder number 4, it's somebody, selling you hair cream or something, on shopping channels or something like that. So each one of those encoders has a different set of processing requirements. Even though they're all being multiplexed downstream to make this, fit into the modulator, each of the encoders has a feedback loop with the multiplexer to be able to speed up and slow down based on what's going on with the content. So when the guy bowls the frame, the camera zooms in as he, bowls the lane, and the pins go flying everywhere. So the encoder is having to work a little bit harder as compared to the guy selling hair cream or whatever. So the point is, there's this thing called what's statistical multiplexing, which is a mathematical process that's used to modulate the bit rate of the encoder based on the quality of the stream as it's being produced by the encoder. And the multiplexer is essentially a calculator that sees this complexity value, and then it computes this value that's sent to all the encoders to tell them to speed up and slow down. So that's how we're able to get so many streams instead of just 2. Now I can get 4 to fit in the same space of where there used to be 2, because statistically, not all the encoders are going to ask for bandwidth at the same time. If they do, they're all going to get the average bit rate across all the encoders. But that's pretty rare, and it's more common that one bit rate will be higher than another, and they'll move around. And so there's this technology out there that does this today. So there's a lot going on, but at the end of the day, you can make it fit. And so in this infographic, it shows this capability to stick 4 different channels in the same space as a 4 or a 2-channel system. So that's a lot to digest. We're going to dig a little bit deeper here because it's all based on math. So digital TV is compression, channel encoding. The compression technology it's based on a codec, and the codec is based on a standard. And so there's multiple standards out there, but the whole point is it was written with must and shall statements. So when you read the document, this is what's directing the decoder designer, how the decoder is expected to work when it sees these bits. So then it constrains the encoder to make the packets a certain way, so it creates compliant output. So as long as there's compliant output from the encoder, then the decoder will go, oh, I know what to do with that. And voila, you get a decoder that works. So the term codec stands for coder decoder, codec, and describes the entire compression methodology, the beginning and the end. So a standard like MPEG describes both the compression and the syntax used to transmit the coded information in a bit stream or a file. So MPEG was one of the first ones that contained all the parts and pieces and mechanisms in a couple of documents, so that when you put them together, it created a complete system solution. So the encoder, it's designed to compress whatever the video input was and audio into a bit stream to be delivered into a digital medium, like IP packets, or into the modulator, which then converts them into waveforms. The decoder is designed to receive that bit stream from whatever the medium was and decode that bit stream. All those bits, those packets mean things to the decoder, to how to modify the picture to get it to the point where it can be recovered to what looked like the original information, the original format. So in video compression, there's essentially two levels, if you will. And these pictures are highly exaggerated, zoomed in on the same thing to talk about those 2 points. One is lossless video. Lossless is all the picture information, which can then be recovered back to original information, but does so at a very low data compression ratio, as little as 2 to 1. So if you were to take a raw picture with your camera and you took the raw data, there is no compression. And the second you do anything with the bits from the raw file to conserve data, you're doing some form of mathematical processing to be able to compress the data down to a smaller file size. That's where the ratio can increase, but the compression, so then the compression gets greater. And so people talk about JPEG. And JPEG is a form of picture compression, and that makes it much more portable to go through the internet. So we're not all sending raw files to each other, because then that would be a horrendous amount of data. So in a lossless video, you see near precision, but it's not perfect because it's still digitized data, but it's got one of the more accurate renditions, and it's not like making up stuff. And I'll explain what I mean by that. And that is, in lossy video compression, it is an aggressive form of picture compression. JPEG is an example. It does not preserve the original picture, but renders a very close approximation, and does so at a very high compression ratio as high as 700 to 1. And so the difference is, when you look at the beak on the left, it may seem a little blurry, but it's very precise. The pixels are perfect. And then what you'll notice is, on the beak on the right, the pixels, there's little funny things. You'll see these little artifacts. They're not perfect, but it's really close. The difference is, the picture on the left side is like 100 megabyte. It's like 100 megabyte original. The one on the right is highly compressed, and it's only like 100 kilobits. So it's a huge difference. So when you look at compressed pictures, you'll see little artifacts. It's not perfect, but it's really close. Now, which one do you choose? There's all these different kinds and types, and there's all different technologies behind all of them. MPEG-1 goes back to laser video disc. MPEG-2 came out as the first highly used broadcast television standard. Then MPEG-4 came out. Now we're working on MPEG-5. It's coming out in the industry. Other companies, they launched a side version of MPEG-4 called MPEG-4 Part 10, or AVC. And if you watch DirecTV, Dish Network, Comcast, all those guys are using AVC. HEVC just came out recently over the past couple of years, so it's pretty fresh ink. But HEVC and AVC are steps above compression efficiency, above MPEG-2. So when people compare AVC to MPEG-2, what they'll say is AVC is 50% better or stronger compression, has better tools than MPEG-2. So at the same bit rate, the AVC picture will look better. And then when you compare HEVC to AVC, HEVC is 50% better than AVC at the same bit rate. And so the picture quality will be better. And what they're doing, and that's why there's AV1 and EVC and LCEVC and VVC, they are adding more and more math processes and techniques to be able to improve the picture quality while reducing the bit rate. And it's all a bunch of math, okay? Same thing is true in audio. They keep getting better and better and better. Audio coding is just not as intensive as video. It's much easier, but it's harder to get better bits at a lower bit rate. It's just, there's diminishing returns. It's kind of like Moore's law. It really spiked over the last 5 years. And so they're getting to the point where they can send intelligent voice speech, you know, you and me talking, and can understand it's me and I can understand it's you. We're getting to the point where we can have bit streams at 2.5 kilobits per second, and it's completely understandable. It doesn't sound like a robot. But that, you know, broadcast quality, you need a higher bit rate. So the lowest we use is probably 16 kilobits, but that's so you can do music and stuff like that. It renders better when you have more bits, but it's a very specialized field just to do audio. So which one should we use? Well, you should use the one that's capable of doing an adequate job at the best price point, cost, and extensibility. We're not talking about performance here. So if you want to make an MPEG-2 encoder, you can. It runs on a Raspberry Pi, and it's using software that's free. And you can probably make it actually do AVC. And it's all based on modules that you get in software that are free downloads. There's tools like FFmpeg and things like that. So you can make an encoder, but now you got to interface it with stuff. But so you can find encoders for cheap online, eBay, you know, on the web, whatever. You can find them, and they're out there. You just need to know what to look for. But you'll spend a few bucks, but those are the appliances that we would use. And so we're talking about this because this is leading up to the conversation of why would you do all this? And it's because you would want to put a repeater together. Okay, so think about the repeater set requirements. Do you want a Raspberry Pi up there? Or do you want one of these encoders that when you plug it in, turn the switch on and set some settings and it just runs? Well, that's more like what you want, because a Raspberry Pi will probably overheat. You probably have to reboot it and all that kind of stuff. That's not very suitable for a repeater site. It's more suitable for us hams to hack on, to be able to use in our ham shacks and to be able to create and experiment and that kind of stuff. And then you can blow it up and then you don't care. But what you put up with the repeater, you want to be a more robust solution. So you can find these parts at the flea market. In fact, I'm going up to Loomis this Saturday, March 19th. They're having the Loomis Ham Fest up there, and it's like the first big flea market. And I'll be up there with my trailer full of goodies. I have a bunch of stuff I'm trying to do. I have to purge now. So since I don't have a job, I have to get rid of stuff. So anyway, the other part of this is you want something that's extensible, that, and what you're trying to do is hit the target on getting this technology to work across the widest group of hams that you can serve. So cost, yes, but you're trying to make it so that all the hams can use it and not disenfranchise, you know, some hams because they don't make as much money. So I know other people that have launched DVB-T systems in the Boulder, Colorado area, and it's based on a particular technology from this guy out of South Korea. Yeah, bully for them. They decided to go that way. But what that did was it forced anybody that wants to watch that signal has to have that DVB-T receiver. And they use a very particular one, and it's this handcrafted unit that's made by this guy. And those are $300. I got a better solution. How about one that only costs like 30 bucks? So what I'm going to point out to you is I'm not discouraging anybody from trying different codecs and different profiles or different modulation. Doesn't matter. But you have to understand, you want to make it so that it works through the repeaters and so that all the users can receive and process the content. So to start with, let's set the bar very low and put it on easy mode. Let's not try to make the bar so high because, quite frankly, I don't want to see you guys in high definition. Standard definition is good enough, if you know what I mean. So in summary, compression is, as you go down the steps, yeah, you need more bits to do those lower forms of compression. As you go up the steps, those are much more highly advanced codecs. You need more processing power. The whole point of this is all of these are free to ham radio operators because guess what? We're not licensed to do broadcast. We're licensed to do ham radio. So guess what? All these codecs, they're free of charge. But so somebody was worried like, well, won't you get sued if you? No, because you're not in the commercial business. So you're free to use it. That's the great part about this. Let's now talk about channel coding. I'll try to speed up a little bit because we're running out of time. Channel coding is modulation. Okay, so everybody knows what Morse code is. It's a form of channel coding. Modulation is you're converting bits into symbols, like in a CW key. When you're turning the carrier on and off, you're injecting information into the carrier. And so a digital bit stream of ones and zeros, those are all mapped into waveform shapes to create what's called a symbol. So you can have more than one bit equal a symbol. So you can have 2 bits, 3 bits, 4 bits, whatever. And then all the bit combinations of turning each one of those bits on and off is then mapped into a waveform shape. And each of the shapes are different. And so at the end of the day, as the data changes, the bit pattern that comes in that bit stream represents all the symbol changes. So if you're watching every chunk of 2 bits and every 1 and 0, 0, 1, 1, 1, 0, 0, as those changes come through, you change the waveform. So, and then you also want to do a thing where you add a process layer so that the information can be, you add some more error correction. So there's things you do to make the symbol that you're creating in the waveform more robust. Now, we have to talk about bit rate versus bandwidth. Why? I'm pretty certain everybody understands the concept of when you transmit CW, you're not transmitting the key signal is not square wave. Because if you do, you're going to make key clicks. And there's a guy that wrote this website. He's got a great explanation. Doesn't take a lot of math. It's easy to understand. It's how the slope changes from going from full off to full on. And the more Gaussian the wave slope is, the least amount of key clicks and the narrower the bandwidth. So if it's a very steep slope and not much like a sine wave, but much more steep and square wave-ish, then you're going to create more sideband energy. And that's what we don't want. Well, so the same is true when you're talking about the data rate to be delivered through a transmitter. It's proportional to the symbol rate. So the higher the data rate, then the faster the symbol rate. And that means more bandwidth. And so the higher the symbol rate, higher the occupied carrier bandwidth. And the reason why is it's simple. The coding technology used to create a symbol modifies the carrier in either amplitude, frequency, phase, or combinations of the 3. When you start manipulating those things in time, you will get, and so as you add more bits per symbol, the higher the density. So in other words, you can have 2, 3, 4, 5. So as you move those bits through, you're changing the waveform. And the faster you change the waveform, then the higher the data rate throughput is. But then, of course, so is the bandwidth. So for example, Qpsk stands for Quadrature phase shift keying, which equals to 2 bits per symbol. It looks something like this. So you have an odd bit and an even bit that come in through the data. This is coming from the encoder. So as a bit stream, 2 bits are fed into this this front end bit splitter, if you will. And so one bit goes to one side, which is a modulated carrier, and then the other bit goes to the other side, which takes that same carrier and phase shifts at 90 degrees. So depending on if it's a 1 or a 0, it'll either be sine or cosine, and one of those is going to be 90 degrees out of phase of the other one. And then you combine those two outputs, there's Qpsk. And of course, the inbound, you do this pretty much the same thing in reverse, but you actually add some integration filters. And so then you get back to square waves, but then you can recover the data. So it's decoding the phase shift, and so there's what's called I and Q. So their top one is the I, that's in phase, and the Q on the one below is 90 degrees out of phase. So it's out of phase. So you take the in and out of phase signals, run it through some filters, and then you integrate. And what that is just a filter to get it back to square. And then you get back to bits. And so you end up creating a waveform in a constellation pattern, which is based on the 2 bits, in which case there's in Qpsk, there's 4 quadrants, 2 bits per symbol, and there's 1 1 0 0 0 1 1 0. And so if it's representing one of those, the signal points in that direction. And then for every 2 bits that go through the system, you're clocking it at a very specific rate, and that's your symbol rate. And that's how fast you can move the data through the system. And as you increase the symbol rate, that carrier waveform flips around to represent whichever 2 bits are being represented at the waveform. And at the end of the day, you'll see these concentrated 4 dots that shows up on the waveform trace, and those are the bits being modulated. Now, I did want to throw a little math at you, so there will be a quiz later. Let's say, for example, so here, based on this formula, you got symbols per second equals, and there you go. And so you do some math. And so what you need to be aware of is every MPEG-2 TS packet is 188 bytes long. This Reed-Solomon, which is part of the forward error correction, it adds an extra 16 bytes to that. So 188 plus 16 gets you 204. The fact is that Qpsk requires 2 bits per symbol, and that there's a coding rate that's inside Qpsk. So they can add more error correction based on that coding rate, where a 1/2 is for every 2 bits that come in, 4 bits of error correction are added. 2/3, 3/4, 5, 6, 7/8. That's just the ratio, where 7/8 is the least amount of error correction, 1/2 is the most. So what that does at the end of the day is it allows you to get a certain amount of throughput through the system. So if you're adding more forward error correction, not Reed-Solomon, but forward error correction, you won't get as much data through the system. So let's use, in our example, we had a 4 megabit per second using 7/8, so the least amount of forward error correction. Do some math. At the end of the day, it turns into 2.48 megasymbols per second. Okay, that's great. But now we want to know how wide it is. Well, we have to do one more thing. We can't just use megasymbols. And there's this thing called Nyquist roll-off. Now, remember I was telling you about that slope? Well, so there's a beta roll-off that we use, and it's typically the 0.25. So you see the one in the green. It's not quite a square wave, but if you see beta equals 1, there is no, I mean, that is like essentially a sine wave. But so it's got the least amount of roll-off. It's actually the worst filter you can have. And so that's the hardest one to do. 0.25 is actually pretty simple, but that's the one where it's going to have some spectral regrowth in the transmitter, because the linear amplifiers are going to get this hash created from all that switching coming from the modulator. So we like 0.25 because it's as close to 0 as you can get. So you're not trying to be a square wave, but you're trying to sneak right up next to it. And you don't want to be like sloppy 0.5 because that's just not strong enough. Anyway, what we had to do though is factor in that roll off to the symbol rate. And to do that, it's a simple math problem. So if I have a 25% roll off, I take the mega symbols, multiply it times 1.25, and there you go. I will have a 3.1 megahertz wide carrier, 3 dB down from the top of the crest. It'll be 3.1 megahertz wide to carry a 4 megabit symbol at 7/8 FEC. So this is cool. Now you know how you can make this stuff fit. And if you want it to be exactly 3 megabits, you just turn the bit rate down a little bit, or you change the FEC, et cetera, et cetera. So you work the problem backwards, so that way you can make them 3 megahertz wide, 3.5, 4 megahertz wide, whatever you want. It's just working the problem backwards. So now what we want to do is you're ready to start modulating with this Qpsk signal. Now here's the reason why Qpsk. So COT stands for commercial off-the-shelf. IRD stands for integrated receiver decoder. And so these integrated receiver decoders are commonly found at earth stations, teleports, dish farms. These are what's used by the commercial broadcasters. The RF input of an IRD uses L-band. L-band is defined to cover frequencies from 950 megahertz up to 2.2 gigahertz. The nice part about that is we just step right through the amateur 1.2 gig band. It's all in there. So the cool thing is these IRDs can operate as low as 1 megasymbol per second. Mind you, we were just talking about 2.48 megasymbols per second to do a 4 megabit signal. So we need them to operate at that low end, even lower in some cases if you want to get super narrow. But so what's nice is you can find these IRDs pretty much anywhere. Some of them can operate as high, very high symbol rates, above 36 megasymbols per second. We'll explain more about why that's significant later. It receives a Qpsk signal to decode the MPEG-2 transport's bit stream and then decode that stream back into video and audio. So it does two things. It receives L-band, listens for the transport stream that's being modulated in Qpsk, pulls the MPEG-2 transport stream out, and then runs it through a decoder and gives you video output. That's why they call it an integrated receiver decoder. It can also inject a bias signal up the wire. That's what's used to be able to drive the LNB or LNA in some cases. And so that's a voltage we can snipe from the IRD that can drive a little LNA for our purposes. Or toggle polarity switches, you know, so in other words, the satellite industry needed all this stuff. It also sends AFC feed, you know, so there's a whole bunch of stuff it does. And we don't need to read that anyway. So the thing is about digital amateur television is it's very effective spectrum management. And so we can, as I populated the thing here, you can see I've carved up chunks of spectrum where one of them is still 6 megahertz wide. That's the green block. But all the other ones are digital and they're chopped up in either 2 megahertz of this one and 1 megahertz and 3 megahertz of that one. And then I've got 2 of them, they're doing stat mux inside of 4 megahertz. It's because you can make them all fit because it's digital and you can change the symbol rate and modify it. So you still want to leave space for the analog guys. So the analog guys can still do analog, but then you can have an analog input on a digital repeater and put that out on your signal too. And then as long as everybody's got a digital receiver, then even the analog guys can operate with the digital guys at the same time. In summary, Qpsk is the lowest cost to deploy since DVB-S, where S stood for satellite. Qpsk is commonly used for satellite links. So it's the widest deployed specification in the world. Everybody uses it. I don't know anybody that doesn't, okay? Even the military. The higher the symbol rate, the wider the bandwidth, the higher the payload capacity. Other modulation forms exist like QAM, which stands for Quadrature Amplitude Modulation. The other one is the other popular broadcast standard besides ATSC is DVB-T, which is used in Europe, and that's for terrestrial broadcast television in Europe. But all the receivers must conform. So you're either going to do QAM, or you're going to do Qpsk, or you're going to do DVB-T. You have to pick one, okay? As I said before, QAM and CoFDM are available, but they don't represent the dominant, most lowest cost, most flexible system solution. And why do I say that? It's real simple. Go on Amazon and look up DVB-S receiver. And they make them in China for dirt cheap, and you don't know how they do it, but there they are. They're like 30 bucks. These other ones that are DVB-T, they cost 300 bucks. Which one would you rather? Now, the thing is, ATSC 3.0, it includes specification for this cool thing that you can do. It's got a dedicated return channel. It's the only two-way TV standard. Now, it's never going to get adopted here in the United States because the FCC won't give broadcaster spectrum for that return channel. The guys in China are the ones that asked for this. And so they went ahead and did that work. In the future, more and more TVs, if they say next gen television on the box, so if you go down to the store, it may not say it on the front label, look on the side label. And in particular, I know the Sony TVs, they've been rolling out with the next gen tuner built in. They'll be easier to find. They'll eventually show up in the store near you. Not everybody's going to 3.0 today, but they will eventually. So it's still very early days. Just wait a few years. It'll eventually, take over and dominate the market. Let's talk about systems, and then I'll go faster. So multiplexing, as I mentioned before, this is a logical conceptual view, if you will, where the MPEG-2 transport stream can be thought of as a pipe carrying a bunch of other little pipes. And inside those little pipes, you can carry channels. And inside those channels, you can have other little pipes, which are the video and the audio and some metadata. This is how it's visualized, where all those packets mean something because they're lined up in a specific way. So the MPEG-2 transport stream MPEG defined how the transport stream is constructed using 188 byte packets. The MPEG compliant transport stream includes structures called tables, and that describes how channels are defined. As well, it also defined how the video is packetized. So the point of that is one video packet is larger than a 188 byte transport stream packet. And so they came up with a way to chunk a 1 megabit iframe into a bunch of 188 byte packets. So it's packetized. But so then they also define tables, which are these logic structures that say which packets represent what video. And so when you turn the channel, you look at this PID, and those PIDs are the IDs for all those packets. And there's 8,200 and some odd packets numbers to choose from. And so they're all labeled. So when you look at a transport stream, all the packets are constituted there to carry the video, the audio, and this metadata. And so you'll be looking at the PIDs. So a transport stream can carry many, many, many PIDs up to the sum payload data rate of the coded channel that you can get through the modulator. So up on the mountaintop, you'll have something that looks like this. So to combine the content from 2 or more channels, a MUX is needed. And so you have all those receivers. So you have one for the 70 centimeter band, one for the 33 centimeter band, one for the 23 centimeter band. You can have another one for the 10 gig band. So you can have all these analog NTSC signals fed to the encoder, and then each of the encoder outputs is then multiplexed together to then feed the modulator, the DVB-S modulator, which then goes out and you transmit that to your IRD. And so the point of this is, in this solution here, we're taking 4 inputs at the same time, all encoded to be carried on one carrier output from the repeater using that bus. So the repeater has a video input. It has an encoder, which then creates a transport stream. So then it's compressed. Then that's fed to the modulator, where you add the forward error correction and it turns it into I and Q. Then that modulator output is fed to the power amplifier, and then that's what's transmitted over the air to your antenna. And then at the home, you'll have your little integrated receiver decoder. It'll listen to the signal, and it will take that signal, tune into it, and then decode the packets, and then turn the packets into pictures and audio. You hook it up to your TV, and bada boom, bada bing, you're done. Now, the cool thing is you can add a digital input right next to the same analog input. Where an IRD can share the same antenna input, you just take that same antenna feed from the, the bandpass filter from the repeater side, and you feed it to both the analog and the digital receiver at the same time. And then what you do is you key the video line from the IRD, so when it's analog, it just does pass through. But if it gets a digital signal lock, it'll switch to digital and interrupt the video going to the encoder. So you can have either analog or digital inputs with every band that you support. So this is a great way to be able to add it incrementally, where when the user base eventually starts using digital, this is how you can integrate it. Obviously, you can simplify this even more, but what I wanted to make certain is that you understand the concept is whatever you feed the encoder it can be analog or from a digital. And so then you can take those signals, put them through the multiplexer, and some multiplexers have more than one output, where you can define two different bit rates based on the different encoders. So I can say the A output is just encoders 1 and 2, but I can have the B output include encoders 1, 2, 3, and the IRD all at the same time. So that way I can put some of the signals on 1.2 at a lower symbol rate and put all the signals on 2.4 gig at a much higher symbol rate. Does that make sense? So which hand band is the question? Of course, we talked about this. The UHF band 427, you only have 6 megahertz. That's it. You're done. The 900 meg band, there's actually 2 different 6 megahertz allocations up here in Northern California. Your information may be different from wherever you're at, but so forth. It's each of the bands. One second. Hey, I'm just wrapping up my talk with another group. I'll be there in a second. Thanks. I have to get ready to go to my board meeting, so I'll hurry up here. So there's all these bands, and as you can see, as you go higher up in frequency, there's way more spectrum to be able to move out and run higher bit rates, put up more repeaters, more link systems. I better speed up. Okay, so this is the cool part. That's the sweet part of the band. That's where you'll find more equipment, where there's more availability. Obviously, getting up to 10 gig is a challenge. Using 3 gig would be great, since if we don't use it, we're probably going to lose that portion of the band to the 5G consortium people. The 5 gig band, it's pretty much like the microwave band. For 2.4, it's the ISM band. It's kind of noisy there, but the more we use it, the better. Any case, that's why we're saying, let's look at these bands. And so you can have an all digital repeater, no encoders, everybody's digital. This cuts the cost down very significantly. The parts are much easier to find, kind of thing. It's the critical part is the DVB-S encoder modulator part. That's the one thing you need to look for. And so as a summary here, greatest advantage of digital is all this multiplexing. Yes, there's latency, buffering, all that kind of stuff. You can't get away from that because it's digital. Adding IRD front ends to an existing system is stupidly simple. And multiplexers sometimes have more than one, and they always have more than one input, and sometimes they have more than one output. So that's cool news. So streaming's changed everything. The internet, I just did an update to my website to talk about this. It's the Zoom effect. you could have a computer on your digital repeater being fed. I could be talking through your repeater right now if you had a Zoom connection up on a repeater, if you had a repeater. And it's simple. You have this video camera that goes into a laptop. You know how streaming works. I'm doing it now. So basically all you needed was the ability to get the internet up to the repeater site. And once you can do that, then you can do this, skip all this. There's a transcoder packager thing that's involved. Okay, so long story short, you can still do the traditional multiplexing, but you can feed them from a computer where that computer can be a ham authenticated Zoom client that's fed from the internet. So then you can take content that comes from Zoom and put it up on the repeater, and vice versa. You can take the content from the repeater and send it to a streamer, so you can stream it into the internet, and so then you can see both sides. Let's just go fast. Any to any, new directions, distribution links. So these are the toys I want you guys to start looking at. These, they're out there. Lime SDR, the Hack RF1, the Edis, Adam, Pluto, all those things. These are the SDRs that run on computer. This will allow you to make a modulator, to make Qpsk, because there's modules inside GNU Radio. And I want everybody to see that link, http:// down at the bottom. See that? www.gcndevelopment.com, GNU Radio index. That is a compiled binary for Windows that runs GNU Radio in Windows. So now there's no excuses with that. With one of these plug-in dongles and running GNU Radio, you can make a Qpsk modulator. Microwave bands, yeah, it's a little political, but let's skip on. Oh, satellites, yeah, good luck. I think there's some hope on the horizon, but I wouldn't hold your breath. Everything's kind of been sidelined and, you know, deposited on the ground. It's a heaping pile of mess. In conclusion, we talked about where we came from, how coding compression works, what the DATB systems and what streaming looks like. We are here about the building blocks of technology. Systems which allow freedom of choice have the most to offer to our ham community, and new systems with more flexibility will include some new challenges. You're going to learn some stuff. You're going to have to pick up the learning curve. Ham radio is all about exploring. So you're going to learn more about what a transport stream multiplexer is, how encoders and decoders work, what a dash packager is, what SDR is, you know, GitHub projects. If you're not familiar with GitHub, that's how we share code, you know, in the open space world. And you're going to probably learn something about cloud and private links, because there's more people leveraging stuff in the cloud every day. So club solution, yeah, we're talking about this because we have this problem of having gone through a pandemic. We're having a tough time restarting our meetings. Everybody got comfortable with Zoom. The problem is our finances for the club took a massive hit, because we used to generate income from raffle sales. Well, that means you had people there to buy raffle tickets, and that went away. And so we're having a tough time coming up with the money, and it's hard to do car washes and, you know, with a bunch of hams. So we're looking at ways to make it extensible, so that way we'll still have a meeting, but we'll also offer a Zoom link from the meeting, and then put it up on the repeater, and then have everybody pick it up off the repeater, as opposed to running up a Zoom bill, because somebody has to pay for Zoom. I want you to guys think about building one of these. And with this, I'll leave you to Dennis. I'm done. I want to say thank you. Here's a bunch of references. If you guys want this presentation, I'm more than happy to share it. You can get to me if you got more questions, more specific questions, or you need some help with some equipment. Just reach out to me on email. But that's it. Thank you, everybody.
All right. With that, I want to say 73s, everybody. For some of you, I'll see you tomorrow. And for the others, I'll see you when I see you. 73s.
Good night, everybody.
See y'all later.
Thank you all for coming.
Night.